Good morning, everyone. We're going to wrap up chapter 6 here this morning, hopefully relatively quickly, then we'll get into some review problems over chapters 5 and 6 ahead of next Tuesday's midterm. There's a review tonight. The normal one by Dr. N is tonight here and also on Zoom. I think it's 6 o'clock or something, but I'll send the announcement today since it's tonight in case you missed it. But it's in a previous announcement, and then my review Monday morning, 7:15 before class. Of course, I'll record and post as usual. If you do have questions, especially if you can't get here right at 7:15, just email me your question and I'll throw it into the slides and we'll review it and you can watch the video when you get a chance to. And then I believe I have a video of all the solutions. If you look, there's a chapter 5 and 6 lecture review packet that's up on Carmen and our lecture page that we'll review here in class as much as we can today. I have videos from the past where I've reviewed those problems I can post over the weekend just in case you saw those questions and want to see them. If you like seeing video solutions, if you go to the daily quizzes and you haven't seen a lot of these, there's video solutions for probably about half the quizzes over chapters 5 and 6 that you can try the quiz, hopefully see how you do, and then check the solutions afterwards. Of course, I'll put the modules up for the practice midterms, for the department level practice midterms, the two that they put up. Those will be available later this morning. I like to make sure that we cover the material. If you start taking a practice exam before you've seen the full material, I don't know how helpful that is. I really hope that you take a practice exam like the real thing to give yourself a chance to take an exam like it will be in the real setting. Remember, one of the things I think happens a lot of times on an exam is it's easy to forget everything you learned if you don't practice like taking a real quiz, a real test in that exam-like situation a bunch of times ahead of time. So that's why I think you have to put yourself in that exam mode. Otherwise, you know that feeling where you feel like you just forget something you know. It's because you just haven't practiced recalling it a bunch of times. The more practice you get with that, the better you'll be. Okay, so let's come back to the configuration that we're asking about titanium here and look at this one more time before we move on. I also wanted to kind of think about calcium first. So let's think about calcium's configuration, then titanium, then we'll move forward past these elements. But for calcium, if we're going from scratch, it just starts with the lowest orbital, 1s2. Just think about going hydrogen, helium for 2, lithium, beryllium for 2, so that's 2s2. And then we have 6 elements across, so we go 2p6. Then we come to a block of 2 elements, that's a 3s2. Then we go the next 3 for a 3p6. And then finally we arrive back where potassium and calcium are at 4s1 and 4s2. So for calcium, a 4s2 would be its ground electronic configuration. So this is kind of the way we would describe kind of the way the electrons are going to distribute in a ground state calcium atom. Let's double check a couple things. Calcium's element number 20, that's the atomic number. And so we should have 20 electrons assigned, and we have 10 here, plus 8, that's 18, plus 2 is 20. So you should always be able to double check the number of electrons assigned or equal to the number of electrons in that neutral atom. In terms of configurations of things like calcium 2+, Cl-, that's actually a topic in chapter 7. So if you're thinking, what about ions and their electron configurations? We talk about those in the next chapter. So don't worry about configurations of calcium 2+, iron 2+. That'll come up in our next chapter after the midterm. And so when we're looking then at kind of like where these electrons are, in terms of their actual, because as I said, the configuration is kind of telling you the location of the electrons. Well, think about kind of what these orbitals look like. Our s orbitals look like they're a spherical orbital. We have a 20+ charge in a nucleus, so a really compact nucleus surrounded by 2 electrons in one s orbital, 2 more electrons in the 2s orbital, and then we have the 2p orbitals, of which I'll show 2 of the 3p orbitals. So you can kind of think between after the 2s electrons, we have that space beyond those orbitals that the 2p electrons are going to use. So they're using this space here to fill into. Then we have our 3s orbital. And that's kind of encompassing the 2s, and we have the 2p set of orbitals. So we have our 2p here, we have our 3p orbitals here, and then finally our 4s. And then where I really wanted to kind of start today with is the thought of, well, why 4s and not 3d? So why do the electrons choose to go into a 4s orbital and not the next kind of subshell after the n equals 3, the 3d? And what you can think for atoms is that they kind of have a choice of, do we go further away and then get further away from that positive charge? Remember, our electrons in these orbitals have a negative charge, and it's that attraction in towards the nucleus that kind of keeps these electrons held into place and these atoms existing with that attractive force between the negative electrons and the positive nucleus. But then if we were to use, let me use a different color, let me picture like a 3D orbital. 3D orbital, one of them might look something like this. We're going to use this space in here. The question is, or the issue is, those electrons in that orbital are going to experience a greater repulsion with the other electrons because they're like being packed into like a closer space. And then you can also sort of think that when we're looking at this space here, that there's probably more space between the 3p orbitals than there was with the 2p orbitals. And so that's why there was no 2d orbitals, was because if we're thinking then, well, what about this space between, these are the 2p orbitals here, what about this space here? Well, that space is more compact. It's harder to pack electrons in. So that's kind of an explanation why there's no 2D orbitals, is because the 2p orbitals are too small to have space in between them. It's kind of almost the same reasoning between the n equals 1 and the n equals 2 levels, that between 1s and 2s, there's just not enough space for the p orbitals to exist. So it kind of gives you an idea that to have p orbitals, we need to jump up like an n value. To have d orbitals, we need to jump up another n value. To have f orbitals, we'll have to jump up another level. It's kind of like the region of space for f orbitals would be in this region here. Probably not a lot of leftover space in between the d orbitals and the p orbitals. But maybe there would be when we get to the next layer, when we get to the next sort of shell. Okay, so for calcium, and another thought would be that when you come up with an idea of what you think the configuration is, you would go check nature. You would then say, well, if calcium could have been a 4s2 or a 3d2, you then kind of can come up with a picture or an idea that if it were 3d2, that it would have had the electrons put in spin unpaired. And the very simple experimental test is, are calcium's electrons spin paired or are they spin unpaired? And its electron configuration is such that the electrons are spin paired. And so the configuration, the energetics of those electrons are consistent with it being in an s orbital. So something that's maybe hard to comprehend is that the possibilities that the atom had, it can weigh those. It can sort of weigh any possibility for configurations that you can imagine. And what we want to do is try to understand, well, what are the most stable kind of configurations that it might have considered? And then what did it choose as its most stable configuration? That's the one we're telling you. And that's like the 4s2 for that outer configuration. And so then the s block elements like calcium, potassium, rubidium, strontium, cesium, barium, they're always putting their last 1 or 2 electrons into an s shell. So we kind of call those 2 blocks of elements the s block elements. If you look at the sort of boron to neon group, those are last putting their electrons into a p subshell, so we call those p block elements. We call the transition metals, the ones that are 10 across, we call those d block, because they're generally last putting their electrons into the d shell or a d subshell. And then lastly, lanthanide and actinides. We'll get to those eventually here today, but those are last putting their electrons into an f subshell. And you can sort of see that because it's 14 across. And so then we go to titanium. Then for titanium, it's like, okay, we filled the S subshell. Should we go to a P subshell? Should we go to another S subshell? What about the D subshell? So we end up filling the titanium configuration as argon, 4s2, 3d2. And so then you're thinking this subshell here in terms of the number of unpaired electrons. You want to think 4s2, 3d2. You want to maximize the use of space, spin pair those electrons. You theoretically could write the spin up in any of the combinations of orbitals you choose, but by convention, we usually choose the leftmost, we usually choose up. But you could have written these, like this is perfectly reasonable to show them down. It's just not conventionally what we tend to do. So that's a perfectly correct configuration. The thing that would be wrong would be to show one of them up. So an up and a down, the spins aligned in the same direction. There's a total spin on this atom as a result of having 2 spin unpaired electrons. The valence count, this is what we were ending with last time. The total number of electrons that are outermost and really important for this atom are these 2 electrons here. So we say that it has 4 valence electrons. This is a nuanced topic because the valence electrons generally are going to be the outermost shell. So whatever's in the highest n value. We'll come back to this for a couple more examples as we go along. But this is a lower unfilled subshell. If it's unfilled, we count those electrons too. And they're going to be really important for us to think that when we start thinking bonding as we get into the next couple of chapters, the valence electrons are really important for us to consider in terms of their interactions with other atoms' valence electrons. Okay, so let's push forth. So what atom has this configuration? So if we're given a configuration like this one, where it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, all we really have to do is count electrons. So we can either count from the start, or we could realize that all of this here is argon's configuration. And we have an argon 4s2, 3d6. And so that's 8 across the row, because we got 2 here and then 6 here. And so which element is consistent with being 8 across? So if we go 4s2 through calcium, then 1, 2, 3, 4, 5, 6, looks like iron. So that would be the configuration of iron. So one of the goals of configurations is we just want you to look at an atom and have an idea of what you would expect its configuration to be. And then we would like to give you a configuration and then figure out what the element is. I mentioned some elements are different than we expected. This gets a little bit ahead, but chromium, we would expect chromium just 2 on the other side of iron. We would expect it to be an argon 4s2, 3d4. So if I said to you on a test, I really wouldn't want to say what is chromium's configuration, because it turns out it's different than what we expect. But I would expect you to know what we expect. You know, the simple explanation for what you expect is you expect to fill the 4s, that lower energy orbital first, and then into the d subshell next. The reality, the actual configuration is argon 4s1, 3d5. And so in reality, it turns out that there are sometimes configurations in certain elements where a configuration is better than another configuration. And so having a half-filled subshell sometimes adds a little bit of extra stability, but not in every instance. We'll go through a chart in a minute and see that this really isn't necessarily always a periodic trend for like chromium's group. So when you get to like molybdenum and tungsten, they don't always follow the same trend. But so we see 4s1, 3d5 as our actual configuration. Now, I don't expect that you memorize the ones that are anomalies, because that's kind of weird. I don't expect that you know all of the elements that do this. I think it's just worth knowing that when this happens, you get 1 electron 4s1, then you have 5 spin unpaired electrons. You have a total of 6 unpaired electrons. So if I give you like an anomalous, anomalous is just like an anomaly, something that's not expected. And so if we give you one of these configurations that's not as expected, you can work out like unpaired electron counts, just like you could if you were given an element and then we're thinking of its expected configuration, because this is ultimately how you determine that this configuration was not right for chromium, is that the actual element has 4, not 4 unpaired electrons, but it really has 6. So that's an experimental observation that you can make using some experimental tests to determine that. Okay, and so we'll come back to anomalies in a minute and look at some, a couple charts that'll show us a whole list of elements and their configurations, so we can see most of the elements in the periodic table have the configuration that we expect, and a few have an unexpected configuration. Let's try to get kind of through the next row of the periodic table. So once we fill to zinc, we're filling the 3D subshell, and then we had filled through the 3p for like aluminum across, so gallium, and across the krypton, I'm going to fill into a 4p. So a real quick configuration might be a couple ones before we get to tin, would be like, let's say bromine. So bromine's configuration would be, it follows argon as its preceding noble gas. And so think argon, and then we're in the 4th row, so it's a 4s2. And then it's not a 4d2, it's a 3d10, because we're filling into that first d subshell, which was for n equals 3. And then we have a 4p5. And so then if we're thinking of a configuration here, I'm probably not even bothering showing the 3D, because this is going to be 5 orbitals all spin paired with 10 total electrons. So I'm just showing my 4s2, 4p5 for 2 electrons, and then spin pairing all but one of the electrons. And so I have 1 unpaired electron. And then in terms of a valence count, the valence count here is not going to count these 3d10, because that's a filled lower subshell. So the idea of valence shell is outermost shell. So the shell is the n value. So the outermost shell is n equals 4, so that should be 2 plus 5 for 7. So I mentioned, valence electrons is a little bit nuanced. I don't think you're going to see too many questions about valence electrons that really get into the issue of like filled versus unfilled D subshells, because that gets a little bit nuanced. It's maybe not that big of a deal, but it's going to be a little bit of a bigger deal later when we get to when we're drawing like Lewis structures in chapter 8. We'll have to make sure then that we come back to this idea that we're counting bromine as 7. 17 valence electrons sounds kind of crazy. So the idea of valence electrons is they're going to be the ones that are most important in bonding. I think I see a question developing here. Yeah. Oh, so why argon? Well, we don't have to. It's just a condensed way of writing the configuration because it's saving me from writing argon's configuration. So if you think of the configuration of bromine, it would be 1s2, 2s2, 2p6, 3s2, 3p6. But so a lot of times what we do is we look to the nearest preceding noble gas and kind of say take that configuration, then add on to it. Yeah, but if you have to, just start from 1s2. And then at the end, just kind of then look and see, well, what element is comprised. So if you're just writing out, 1s2, 2s2, 2p6, 3s2, 3p6, that's what we mean by argon. Now, when we get to tin, we can, I think, hand wave through getting to tin. So, once we get across bromine, we then get to krypton. So the next row's configuration, like rubidium and strontium, could be krypton, but then 5s1, 5s2. And then we're just going 4d1 for yttrium, zirconium, 4d2, niobium, 4d3. So we're just filling across the 4d subshell. We get all the way to cadmium underneath zinc. That would be the 4d10. So if we're doing tin's configuration, it kind of takes us from krypton, then the nearest preceding noble gas. And then in terms of the next kind of thought would be, I think you would know it's an S2 next, and then what S2? Then you can just realize hydrogen's a 1, lithium's a 2, sodium's a 3, potassium's a 4. So we're now into the 5s2. And then I think the next issue is making sure you get the right number in front of the D. And then we're going all 10 across the D subshell. But then the 3D is the scandium across, so the yttrium across would be the 4D10. And then we're ending, tin is in the row of carbon. So just to make sure you see we're SN element 50. So we go indium and then tin. And so tin would be back to a 5p2. So how do we know that's a 5? We'll just come back to what you know carbon to be. Carbon's a 2p2, so silicon would be a 3p2, germanium would be a 4p2, and then tin would be a 5p2. So if you get stuck on what the numbers are, just come back to the ones you know. Come back to carbon's a 1s2, 2s2, 2p2, so it's 2p. So we have, and one of the next slides will show you, we have the 2p, then the 3p, 4p, now we're into the 5p group. And so then our valence diagram would just include the valence orbitals of the 5s and the 5p. You could show the d, but I don't think it's really all that useful to show the 4d because you're just showing 5n, the other 5, so you're showing 10 spin paired electrons. So they're really not part of the valence diagram, so they're really not counted towards the valence count once that subshell is complete. So then we have a 5s2, 5p2, just looks like identical to carbon in terms of that configuration of having 4 valence electrons and then 2 of them unpaired. So 2 unpaired electrons, that's these 2 here, and then 5 valence. And the valence is going to mean all 4 of those electrons participate in bonding when tin's going to participate in bonds with other atoms. So then let's look at this page here. So this is what the periodic table would look like if we could have a periodic table that was just very long. And so these elements here are just conventionally taken out of the periodic table and shown down here so we can remove them and then zoom in a little bit. And so it's really nothing but for aesthetics that the F group elements are shown where they are in the periodic table. And so if we could wedge them in and slide the periodic table down and have a longer piece of paper, then that would probably be the ideal way to show the periodic table because it really lets you see how you go from the 1s block to the 2s block to the 2p block to the 3s to 3p, 4s, through the 3d, then through the 4p. And think about how nature is really the one that's kind of accessing these orbitals and determining for us what these relative energies are. I was thinking about this from a question I had the other day of just what would it have looked like if the 3D was a lot more stable than the 4s? If this row was so much more stable, then it would have come up here, and then we would have filled the 4s next. Like potassium and calcium as properties probably would have had an extra 10 electrons in them if it were the case that the 4s were a lot higher in energy than the 3D subshell. But it just turns out the 4s is a little bit lower. It's filled first, and then we fill the 3D. And so then we fill the 3D, then the 4P, then we're back to the 5s. This is where we were just at for 10 right here across that 5P subshell. And so then if we continue into bigger elements, cesium, barium would be 6s1, 6s2. And then if you kind of follow the periodic table, this one's a little strange on the wall because it goes lanthanum and then down below cerium across. And so a few periodic tables do this a few different ways. A few of them leave this element here and throw these down here. The one you get on the test actually throws and leaves a blank. So if you look at the one you get on the test, it actually takes all of the 4F elements and it actually wedges out these elements here, throws them below, and then kind of leaves a gap in the periodic table to kind of give you a clue of where the gap in the table is coming. If you follow, the easiest thing to do is to follow the atomic number. So follow 56 to 57 to 58, and then you'll see you go across the F block, and then you come back up to hafnium at 72, tantalum 73 on across. And in terms of name and symbol, you get to a point once you get really through the fourth row that we kind of stop expecting you to know the name symbol pairs for a lot of these elements that aren't that common. So don't feel like we'll throw you a lot of examples where you have to have, like if we said like tungsten, you may not know that's W. I probably wouldn't expect you to know that. But a lot of times what we might say is like tungsten dash, its mass number. So we do tungsten dash 74 or show you W74, kind of clues you where to look. So when we're giving some of these bigger elements, kind of look for us in a problem to sometimes clue you in on where to find it on the table. And so if we were trying to do the configuration for something like tungsten, how would we do that? So tungsten, if I get it right on the table here, should be 1, 2, 3, 4 across. So tungsten is right here on the periodic table. So how would we get to that configuration, either from this periodic table here, if we're looking at this, or the one on the wall? Well, I think the first thing you would do is say, well, what's the preceding noble gas? So if you go all the way back, the preceding noble gas would be xenon. And so the configuration for tungsten 74 would be the configuration of xenon. Now xenon would just fill that 5p subshell. So if we go back to tin, so tin was the 5p2, xenon is just the 5p6. So we got across the 5p. So then the next shell down would be cesium, barium, 6s1, 6s2, so that's a 6s. And then we're filling 14 across the F block. Now why is that a 4 and not a 5 or a 6? Well, we have to think, well, what's the first time you can have an F block? F is L equals 3. The first time we can have L equals 3 is when N is equal to 4. So the first time we can have that F block is the 4F. So the first F block is 4, just like the first D block was 3, just like the first P block was 2, the first S block was 1. Okay, so 4F14, and then 1, 2, 3, 4 across for a 4D4. Or excuse me, not 4D, this would be a 5D4. Now, how do I know that's a 5D4, not a 3 or a 4D4? Well, it's just kind of realizing that the 3D was here, the 4D was here, so the 5D is the next row that we're filling into there. So it just kind of comes back to scandium across is 3, yttrium across is 4, so lanthanum across, or that group there, would be the 5. So 5D for 4. And so then if we're thinking of valence diagram, I'm just probably picturing the 6s2, 5d4, filling in our electrons. I'm skipping the F block because it's filled, but I could write 7 F blocks and with 2 electrons in each of those orbitals if I really wanted to. And then we would continue to the 6p to the 7s across the 5f. And then once we get past uranium, so the transuranium elements, notice how the font changes. That's because those are no longer elements that we find on Earth. So those are elements that we have to synthesize or create by man-made processes. And so anything beyond uranium had existed, or a lot of those elements had existed from the Big Bang and just had decayed over time to where we're at right now. So if we could flash forward another billion or 2 billion years into the future, we likely wouldn't have very much uranium on Earth at that point, even if Earth exists at that point, who knows. But if Earth were to still exist as a planet in a similar way to now, a lot of the big elements now would have decayed into smaller ones. Uranium is always decaying, but slowly into things like thorium, and then from there on downward. So what happens to a lot of elements that are bigger is they lose a helium nuclei and become smaller. That's a topic for nuclear chemistry that you might see in Chem 1220. But I think it's interesting just to kind of understand that anything past uranium has to be man-made. And we have, not we as in me, but as in scientists actually created all the elements through the periodic table. We should reprint this periodic table because there's names for all the elements. Just in case you didn't know this, when you see like the UUQ, like that's a name you give an element you think exists before you for sure prove its existence and show it in a laboratory. And so once you, as a scientist, kind of discover an element, you get to name it. Or the international applied union of chemists who is in charge of naming things gets together and they decide on a name. And so every element through 118 does have a name. Because they've all thus been discovered. In fact, now they're trying to make things past the 7th row. I don't think anything that's created will be of any importance. In fact, a lot of these elements that they've created, especially the ones like the last group underneath like thallium, lead, bismuth, those elements there, they're so useless and they're practical because these elements exist for such a small fraction of time, but physicists really like to try to see what they can bombard together and have happen. So it wouldn't surprise me if in the next 5 or 10 years you see a discovery of something in the 8th row and we have to somehow maybe consider expanding into an even bigger periodic table. But as you can see, we haven't been too eager to change to the one we have today, so I don't know if it would practically mean any difference for general chemistry. But so let's take a look at some atoms configurations, and what I want to do is just kind of zoom in on a few to kind of show the anomalies, the ones that aren't as expected, or maybe like we should first make sure we see things that actually are as expected, like calcium is exactly what we expected, scandium, 3D1, 3D2, 3D3, so going good so far, but then chromium had that anomaly that we talked about. So know that the anomaly doesn't create or destroy electrons, it just moves one electron from one orbital to a different orbital. And then you don't have to memorize when this happens, but it turns out chromium is one of these anomalies in the first group. Should have been a 4s2 3d4 from our expectation, but really ends up being a 4s1 3d5. So if we give you an anomaly, like if you notice manganese is as expected, same thing with iron, cobalt, nickel, and then we get to another anomaly, copper. If I just said an element has a 4s1 3d10, I would just want you to tell me that's copper. And you can tell me it's copper just because you can take 18 electrons for argon, for its configuration, add the 1 for the S plus the other 10 for the D, and you come up with 18 plus 11, that's 29 electrons. That should be the 29th element of copper. So you should just be able to see a configuration, count up the electrons, tell me what the element is, or if I give you the element, just be able to predict the expected configuration. If you then look at the like say molybdenum, is the trend of chromium periodic? And you can see it is for molybdenum. Molybdenum has the same anomaly that chromium has, but tungsten doesn't. And then see bohrium doesn't either, but that's a weird issue. Once you get into these man-made elements, they exist for such a short fraction of time. I don't think they really know anything about these electron configurations. But setting that aside, tungsten's configuration is exactly as expected, so it's not even periodic for this group here. If you look at the copper group, it actually turns out that that trend is periodic for silver and gold. Again, I don't expect that you know that, but in another case, that periodic trend is consistent through the group. But then look at the nickel, palladium, platinum group. So nickel is as expected. Palladium has a completely different configuration. It should have been a 5s2, 4d8. Instead, just like nickel is a D8, instead it became a D10, where it took those S electrons and moved them into a D subshell. And so then if you look at platinum, it for some reason moves one of the S electrons, which kind of makes no sense at all. And so this trend here is completely without any periodic trend. In fact, each element has a different trend within those three elements. And so that's why I say there's really no point in memorizing which elements are anomalous because there's no real pattern here to these anomalies. And then if you look here, ruthenium and rhenium have some weird configurations where they're, instead of being a 4s2, 3d6 or 7, they're a 4s1, 3d7 or 8. Again, why do they do that? I have no idea. They just happen to have those anomalies. Now, one thing that's worth knowing and kind of coming back to is these are the configurations for these atoms if they exist as a monoatomic atom, so a gaseous atom. Once you have a solid atom, things can change. But this is just looking at the properties of a single isolated atom and what their configurations are. If we then inspect our p block elements, we see that you see in every case it's p1 through 6. So there's nothing really interesting going on in the p block in terms of anomalies. All those configurations are exactly as we expect. So we just see a couple weird configurations for things like chromium, molybdenum, ruthenium, rhodium, for palladium, platinum. And so I think those are most of the anomalies. But again, not worth memorizing, but just knowing that these come up sometimes. And the issue is that whenever these arise, the conclusion you can make is it must be the case that the 4s and the 3d subshells are very similar in energy. And so if you think of the difference between like the 2s and the 2p, or the 2s orbital and the 2p subshell, they're very different in energy. There's no promoting electron to a more stable configuration when there's a big difference of orbital energies. Remember how the Bohr model starts, the energy levels get closer together the higher up we go? This is an artifact of that. You can also see some configuration anomalies within the F block. So a lot of times, like, for example, the 4F should come next. So these should have been a 4F1, this is an anomaly. Cerium's an anomaly. Look how it's an F1 but a D1. So it should have been an F2. We would have expected it to be a 4F2. Praseodymium, a 4F3. Neodymium, a 4F4. Promethium, we would expect that to be a 4F5, which it is, 4F6, 4F7. And then gadolinium is unexpected. So you see a lot of these anomalies popping up in the F block. So it must be the case that the 4F and the 5D subshell is pretty similar in energy. So it seems like we're coming out with the 4F are more stable though. You can see most configurations have electrons in that 4F subshell more so than the D subshell. And so then if we go across the periodic table, 4F, and we see that we're filling that into the F subshell almost exclusively. And so then when we get into the last row, same issue with actinium being a, yes? So elements in the same group tend to behave similarly, but not always. And so it's often the case, this is how we ended up discovering the periodic table before we even knew anything about things like atomic number, before we knew anything about electrons, before we knew anything about electron configurations. So before we were able to really come up with the why elements behave the way they do, we were able to come up with a lot of elements behave similarly. Probably the biggest group of the alkali that behave similar because they all have one extra electron over that valence shell, and it's very easy for those elements to lose that one electron. We saw lithium, sodium, potassium into water all reacted very similarly. But if you then look at some of the properties like chromium, molybdenum, and tungsten, they're going to vary a little bit based on those configurations being slightly different. So not everything is always the same just because they're grouped together. If you then go to like the halogen group, you go gas, gas, liquid, solid, that's pretty different. But they also then are behaving very similarly in terms of all being non-metallic. If you then move into a group like phosphorus, you go through the range of being non-metal, metalloid to metal. So you go from being like a soft, not even solid at room temperature, to kind of like a weird set of properties of semiconductors in the middle to then being a conductor at the bottom. So it really all depends. There's no one clear answer to say that elements in the same group behave similarly, just that there are some things in common, but there also can be a lot of things that are different too. But I think the key is seeing that in terms of if you're just looking for anomalous configurations, you see them in the D blocks, and you see them in the F blocks, and you don't really see these anomalies anywhere else. And so I was just going to lastly point out that you're kind of seeing some of these issues. Instead of being 5F subshells, you're seeing some elements or electrons being passed into the D subshell.
About the row 5, when you were talking about how quantum numbers and number of valence electrons, I had a question about palladium and rubidium.
Yep.
How many valence electrons?
Oh yeah, that becomes a tricky question. And there's probably, we're probably not even going to ask you the question on the easy one. Like if you say chromium, how many does it have? Probably 6 would be the best answer, right? Because you'd have either 1 or 2 in the S, either 4 or 5 in the D, but either way you have a 4s2, 3d4, or 4s1, 3d5, so that's 6. So that's pretty easy. We probably won't even ask you that question. Once you then get into like copper's weird too, because you would think probably 1 by our rule. Usually once you fill a subshell, we stop counting it. So I would probably say copper has 1, but I probably wouldn't ask you the question. And it also is kind of wrong, because we know copper commonly forms a +1 and a +2 cation. So sometimes the trends help us understand some things that we've learned. Like, for example, do you remember how zinc only forms a +2? That was one of the weird things in our naming, where it's like, well, apparently if I say zinc chloride, you just have to know that zinc 2+. And that zinc's a weird one where we tend to not use a Roman numeral for 2, even though I think we should. But our book makes this issue where it doesn't call zinc 2 zinc 2+. It assumes that we know that. Well, once you see it's a 4s2 3d10, the 3d10's filled, it only has 2 valence electrons. So it kind of helps us understand that property of zinc. But to come back to your question, if you're looking at palladium 4d10, I would have no idea how to think of how many valence electrons it has. I probably would, like I said, just never ask that question. Because I think the best answer would be 18, and that just doesn't mean anything. You know what I mean? Like, I want a valence question, or when I start thinking, for palladium, the way it behaves, those d electrons are probably gonna be the ones that matter. Probably not all of them, but certainly not the s and the p electrons. So by rule, probably 18, but not a question we would probably ask. The valence electron question is usually very loaded. What I think is always going to be the case is if you look at, like, aluminum has 3, silicon's group has 4, phosphorus has 5, 6, 7, 8, and then 1 and 2 for the alkaline, that if you just think of like carbon having 4 valence electrons, anything in the row of carbon should have 4 valence electrons. And then anything in like the chlorine halogen group should have 7 valence electrons. And so the take-home message there would be for what we call the main group elements, that you can just look at the position on the periodic table and determine valence counts. That'll be kind of what we use more for Lewis structures, and we get to those in a later chapters. I'll just be looking at something, like let's say we're doing something with iodine. I'll just be like, well, it's in the halogen group, so of course it has 7 valence electrons, and not even really overthink it too much. I'll just be thinking, well, chlorine has 7, fluorine has 7, so too does iodine. Okay, so the last slide from chapter 6 kind of just comes back to chromium, but I also was just jumping ahead and talking about it kind of ahead of time. So chromium has this 4s1 3d5 configuration, so knowing this allows us then to determine that it would have 1, 2, 3, 4, 5, all 6 of its valence electrons as unpaired electrons. Now, the reason why we ask unpaired electrons is because you can test that experimentally. That's something that maybe isn't obvious when we're asking it, is that's like the experimental test. A lot of times, like if you then said, well, go look in sort of an experiment that can count up and determine unpaired electrons, and it has 6, and it's something you can test experimentally and be backed up. And it doesn't really have 4 like you would have expected with the 4s2 3d4. Okay. So with that, let's kind of like head back into some review questions. We have about 15 minutes or so left today, so let's see what we can kind of come back to in chapter 5. The way I mentioned this a little last time, you're going to see chapter 6 equations on your equation sheet. As soon as I put the module up, you'll see them. For the practice midterms for 3, we'll show you on your sample info pack. You're getting most of the chapter 6 questions on the packet. You're going to see equations that look like this, though you're just going to see the equations themselves and not any explanation of what the equation is, but you'll see the equations that are shown at the end of the chapter for chapter 5 within question 1 on your exam. And so most of these equations aren't necessarily equations that we solve things with. So, like we never really plugged in and solved for a force to move an object a certain distance. So these are equations, a lot of these are equations we use as ideas. So like work is the energy it takes to move objects. Electrostatic attraction and repulsion is described by this equation here. So 2 oppositely charged particles brought together, they go down in energy. If we have 2 like charged particles, they go up in electrostatic potential energy. If you have 2 cations that are somehow close together, if you separate them, their energy drops. If you had a plus and a minus charged ion, opposite charged ions, if you separate them, the energy goes up. So just kind of like we get that a little bit from either just a thought of what plus and plus or minus and minus or plus and minus particles would do relative to each other, or you can think of this equation just wanting plus and minus to allow the energy to be negative, plus plus negative negative would make the energy positive if you bring those atoms together. Delta E is being final minus initial, just a conceptual idea. Delta E is Q plus W. This is kind of like a relevant equation to remind us of what we mean here is like delta E of a reaction or process is equal to the Q reaction plus W reaction. You could have delta E surroundings is equal to Q surroundings plus W surroundings too if you wanted. But the key is like the energy change of a process is equal to its heat and work change. And then this usually would become a question of interpreting signs. And so like heat lost by a system is negative, heat gained by a system is positive. Work done by the system on the surroundings, moving the surroundings is negative for work, because that's like if you heat up the surroundings, that's Q negative. If you move the surroundings, that's W negative. So I like to think of those, how those are kind of analogous to each other. And then if you have heat added in, so your heat goes up, that's Q positive. If you have work absorbed in, if you have like a piston contract onto the surroundings or onto the system from the surroundings, if the work is done by the surroundings on the system, then that would be W positive. And so any question that relates to calculating a delta E given Q and W is usually intertwined with interpreting the signs of Q and W. H is equal to E plus PV is just an idea that helped us to sort of, along with work is negative P delta V, that allowed us to derive the delta H expression here. So that just was a helpful equation to let us see that the delta H, the enthalpy change, was the heat change for a process at constant pressure. And then we were talking about how the delta H is approximately equal to the heat change for a constant volume system. And so heat is just loosely defined by the delta H is the heat of reaction of either exactly being the system at constant pressure or approximately to it for the constant volume system. And then Q is equal to MCS delta T is just an equation for a given substance to raise its temperature has to absorb heat. And so this is not necessarily the equation you use for calorimetry. So for calorimetry, we're coming back to Q reaction is negative Q surroundings, and then the Q reaction is negative MCS delta T of the solution that is the surroundings of the reaction. So you have to pick up this minus sign. You don't see this in any of the equations here for coffee cup calorimetry. So none of the equations on this packet or in the back of the book are related to coffee cup calorimetry, but it just has to come back to Q reaction is negative Q of the solution. The Q of the solution is MCS delta T. And so negative Q surroundings is negative MCS delta T. And so we just have to have this negative sign out here for our calorimetry. So this is the equation we would use here for calorimetry problems. And I'll try to squeeze one of those in before we leave here today. And then just a few more equations here on bomb calorimetry, which we don't really look at. We give you the equation just because it's in the back of the book, but we don't really do bomb calorimetry problems on tests that often. We kind of skipped over it. There's actually one in the packet that, I don't know, maybe in the video that I'll post after class, you can watch that if you want, but it's probably not something to worry about for the test. It's actually a very simple problem in a way. If I showed it to you and we reviewed it and spent 10 or 15 minutes on it, you might then come back and say, oh yeah, that actually makes sense. But I don't know if it's worth that 10 or 15 minutes though. And then we have like the sum of the products minus reactants enthalpies of formation for delta H of reaction, but then also the sum of the bonds broken minus form with bond strength. So just know bond strength is flipped. It's the reactants minus the products. Okay, so let's try to get into a couple problems here before we take off. So a balloon is filled with air at room temperature, then it's immersed in liquid nitrogen. So we have a balloon at room temperature, we then put it into liquid nitrogen, and so what do you think is going to happen? It's probably going to contract, right? So you can imagine the balloon is going to contract at that lower temperature. And so what is the temperature? The liquid nitrogen's temperature turns out to be 77 Kelvin, just so you know that that's definitely cooling the balloon. And so what happens to the sign of Q and W for the air inside the balloon? So the air inside the balloon, its temperature drops because it goes from room temperature down to 77 Kelvin. And then the volume is dropping inside the balloon because it's going to contract. Because the balloon, we're even told that the balloon shrivels up, becomes smaller in volume is what that's telling us. And so the temperature dropping, did the air absorb heat or did air release heat in the process? So did air gain heat or lose heat? It lost heat as it dropped its temperature. So the heat of air dropped, and then did the surroundings work on the balloon or did the balloon work on the surroundings? So expansion is generally what we think of as being work done by the system. Contraction is what we think of as the atmosphere working on that system. And so this is the system absorbing work. So work should be positive. If the balloon was doing work, it would be pushing into the surroundings, and then that would be negative. Okay, so work done by the reaction is negative. Work done on the system is positive. Yes?
Would work not be, okay, so the surroundings become hot.
Well,
the surroundings become hot.
Yeah. So, and that's one of the tricky parts of this question is that it is not then relating to the surroundings. Because we've done a lot of problems where we say in a different context, like we've said, like if you put something into water and the water's temperature drops, what does that mean about the reaction? And that becomes like a system versus surrounding problem. And so the liquid nitrogen container is kind of like the surroundings. So you can imagine we put the balloon in there, the liquid nitrogen or something probably raises in temperature to counterbalance the drop in temperature. But we're just saying for the air in the balloon, did it lose heat or gain heat? Okay, and so that's why we see the temperature of it dropped and then its heat dropped as a result. So this becomes just a Q is equal to MCS delta T problem just for that air. So temperature dropping, its heat dropping, and then shriveling up being contraction.
I understand what you're saying, but just to help you kind of conceptualize it, if work is being done on something, that means energy is being put into it, because work is just energy, as a form of energy, and energy is heat. So if work is being done on something, how can it become colder?
Well, so work being done is not heat in the form of heat energy. So it is, you're right, when you say work being done on the system, is it absorbing energy, but not in the form of heat? Or it could have been in the form of heat, but it's absorbing it, not necessarily what leads it to have a heat change, but allows it to have a movement change. Just like when you use your car engine to move your car, you're using what would have been heat energy otherwise, but since you moved the car, it didn't heat the engine block up as much as it would have.
A force had to act with a little bit contracted, and
Yeah.
therefore F over D with some positive value.
Yeah. Okay. So we should just be negative on the Q and then positive on the W. Let's look at a few of these problems here. So what changed below leads to a release of energy. And so if we separate two cations, it's a silly idea because I don't know how you bring two cations together, but if you have two positively charged particles, you separate them, energy is released. So our plus plus would be way up here. If we could release them and have them further separated, that would be better. And so that should lead to a reduction in energy, kind of like the opposite of if you bring them together, you increase their energy. So if you have brought them together and then separate them, you then can lead to a release of energy. So that would lead to a release of energy. Breaking a chemical bond always requires the absorption of energy. And so if we want to take a bond like H2, O2, whatever, if we want to break the bond, that bond has to absorb energy. So bond energies are always stable. Bond energies are always positive. If you go back to our bond strength chart, none of them are negative. They're all positive because all bonds are forming because they lead to a net stability. And so it takes energy to separate bonds. And then bringing anions together requires the absorption of energy. So it'll just be A. So the salt dissolving into water then leads us into a thought of like Q reaction versus Q surroundings. And so as salt dissolves into water, the solution temperature drops. The temperature of the solution dropping is the surroundings. So that's the surroundings temperature dropping. So if the temperature of the surroundings drops, that means the heat of the surroundings dropped. So the surroundings lost heat. And so where did the heat go? The heat went into the reaction. And so the Q surroundings is equal to negative Q reaction. So if the surroundings lost heat, it had to go into the reaction. So the Q reaction should be positive. So the surroundings lost heat, less than 0. The reaction gained heat greater than 0. So the reaction would be endothermic. So an endothermic reaction taking place in water is the solution temperature dropping because the heat was absorbed by the reactants to allow the reaction to take place. Now the heat was absorbed for it to change chemical bonding nature, not for it to change its temperature. That's the thing that's maybe confusing, is that when a reaction absorbs heat, it doesn't mean it changes temperature, it just means it uses that energy to break and change its bonds to their energies. And then since it took energy away, the temperature drops for the solution it took place in. Okay, so that should be Q surroundings less than 0. So there we go. So a blank delta H corresponds to a blank process. So exothermic is negative delta H, endothermic is positive delta H. And this would be for like the reaction itself. And usually we wouldn't say delta H of the surroundings. That doesn't make a whole lot of sense. So the delta H of a process or reaction is exothermic when it's negative. So negative is exothermic and then positive is endothermic. So that would be B. Which is endothermic? So phase change, so if we're thinking melting versus freezing, so if we have water solid going to water liquid, obviously ice, if we have ice, it's cold. The cold ice has to be brought to a higher temperature so it can absorb heat. And it's for it to absorb heat means that's endothermic. So ice melting is endothermic. Water freezing, the water has to release its energy that it has. Water's moving around with kinetic energy from its motion, has to freeze down those motions and lose that energy. So that's exothermic. And then water to boil, liquid water, just like solid water, has to absorb heat to break those bonds in order for it to boil. So that's a check mark as being endothermic as well. And so then A and C are going to be the answer. Now, what about hydrochloric acid and the base, the barium hydroxide being introduced together? The temperature increases. A reaction that increases in temperature for the surroundings of the reaction, so the temperature of the surroundings increases, so the heat of the reaction dropped, so that's an exothermic reaction. So A and C for number 4. The state function question, so what that means is path independent. So path independent functions are things like delta H, things like delta E. Q and W for a reaction, depending on how you carry a reaction out, like your combustion reaction, it has octane when it burns releases so much energy, but the energy can be in the form of heat or work, some combination of the two. So heat and work are the non-state functions, those are path dependent. So heat and work are the non-state functions. Heat and enthalpy, so heat's not a state function. Internal energy, enthalpy, that's looking good. Pressure, internal energy, I never really liked this question, but because pressure is a trickier one to kind of think about on how pressure is, like the amount of gas that you end up creating is related to the heat of the process, so a different temperature would have a different volume, therefore a different pressure, so D is not going to be the answer. Internal energy is what we mean by E, so delta E and delta H, those are our state functions. Never really been a big fan of that particular question because the pressure choice is kind of awkward. But let's try to at least wrap up with the question below here, because this gets at a calorimetry question. So in 6.6 grams of a solid compound, sodium chloride dissolves into 100 grams of water in a calorimeter where we know its temperature change. Can we calculate the delta H of solution for the process of the compound dissolving? Real quick, the reaction would just be calcium chloride, CaCl2 solid, going into water, and then ionizing the calcium 2 plus, aqueous, and then 2 chloride ions, aqueous. So the reaction itself, pretty straightforward of what's going on. And then the way we would solve this process is try to calculate the heat change of the reaction is negative Q surroundings. And the surroundings is the solution, described by the MCS delta T of the solution. So we have the negative M, but of the solution, so that's going to be the 100 grams plus the 6.6, so 106.6 grams. And again, it's because we're using the entire solution. And then times the CS, we're told to assume that it's that of water, 4.18 joules per gram Kelvin. And then times the delta T, the final minus the initial, which is 34 minus 23, that's 11.0 degrees C. The degree C canceling is fine. Remember, it's a delta T. If you want to convert to Kelvin, convert the temperatures before and after to Kelvin, then take your delta. It's 11.0 Kelvin. And then when we do this multiplication process here, when I do 106.6 negative times 4.184 times 11, I get negative 4,901. And the units would be joules. So that's joules for this process, but it's for the process specifically for the reaction occurring in that calorimeter. When I go to calculate my delta H of either reaction or solution, notice that we're usually asked in kJs per mole of something or per gram of something. So we want to know the kJs per mole of the calcium chloride. And so this is the joules per 6.6 grams of the calcium chloride. And then if I convert to kJs, I just need to make it 4.901. So I go to kJs is pretty easy. So if I go 4.901, divide by 1,000, and then divide by 6.6, that's the kJs per gram. And I just need to convert to moles. And so I just need to use the 110.98 grams per mole to go to per mole. So times 110.98 would be 82.4, or call it 82.5 kJ per mole. Okay, so a problem like this is think of the reaction in the calorimeter, and then think of then going the heat per quantity the reaction actually took place. This is only 6.6 grams reacting, then go to per mole. Okay, so we're just going joules or kJs per gram to then going to per mole. Okay, guys, I should be able to post the remaining solution so you can look them up over the weekend. Yeah. Should be negative, yes. This is negative.